All right, so in my opinion, one of the best ways to study for the diploma is to try as many old diploma questions as you can. So this is why I often do diploma questions as practice for specific topics. But here I'm going to go over a release diploma, and you can find this online and you can find other ones. And what I like about it is that if you do look through it, it does come with a key, so you can check your answers, which I think is very important. And then the other part is if you were ever marked on outcomes, it also tells you what outcomes that each question represents. If you're not marked on outcomes, don't worry about it. At least you still have the key, and we can go from there. Now, as I go through this diploma, I will try and give hints and tips and things that you'll often see, and I'll get started now. So this first question, we're starting with a thermochem unit, and it's showing that you know the difference between photosynthesis and cellular respiration. So you do need to know those two reactions. You need to understand them and the states of water within them. And sometimes an equation might be nice to you, or the diploma might be nice to you and give you the equation, but you can't rely on that. So these reactions you must have memorized. So the best answer here is going to be C. The products of the equation for photosynthesis are the reactants in the equation for cellular respiration. So as we know, the two reactions are similar, but they're in the reverse order. So we definitely want to know that. Now, the other type of question that's very common is enthalpy diagrams. So with this diagram, we want to remember if your enthalpy goes from reactants to products and you're moving up, that is showing an endothermic reaction where your enthalpy is going to be positive. So now we can answer those questions. So the first one, the net enthalpy is represented by 1. That is not true because your enthalpy is always between the reactants and products. So that's going to be showing with 2. Activation energy will have a positive value, and your net enthalpy will be positive. So our answer here is 2, 3, and 5. Going on, hopefully getting a little bit harder. So this one, what I like to say with our text boxes, in chemistry, unlike bio, they're not always related to the question. So read the question first and then figure out if you even need the text box. This one, I believe you do. It's telling you the calorimeter that would have the greatest change in temperature would be the one containing the enzymes from blank, and the manipulated variable in this experiment is blank added to the contents of each calorimeter. So we definitely need to read the question. So in each of these, we have glucose, and then a different enzyme is being added, right? One is yeast, one is a muscle cell, and then with this, and what your question is, or your text box is showing you, is that based on the enzyme, you'll get out different products and different enthalpies. So when you're asked which one would have the greatest temperature change, it would be the reaction that provides the greatest enthalpy. So that would be the first one, the muscle cell. So we can rule out C and D. And then about the manipulated variable, the main difference between these two reactions within the calorimeter is the type of enzyme. So that is what's being manipulated. And so that would be B. If you are doing these type of questions, and as you can see, you definitely need to know the difference between manipulated, so what you're changing, responding, what you're measuring, and in calorimetry, that would be temperature. And then the last one would be controlled. What are you keeping the same? So those type of questions can have different ways to ask them, but as long as you know what manipulated, responding, and controlled are, you should be able to figure it out. Now, number 3, in comparison to a reaction pathway without an enzyme, the activation energy of the pathway provided by the enzyme will be blank, and the value of delta H will be blank. So we do know that both of those equations had an exothermic graph. When you are filling in your activation energy, it would look something like that, and this part wouldn't be here. Now, with that, if you have a catalyst, which is another word for enzyme, it lowers the activation energy, right? It's providing a faster pathway, and the lower the bump, then the faster the reaction. So enzymes will have a lower activation energy, and delta H is always the distance between reactants to products. So that doesn't change whether you have an enzyme or not. So this one looks like our answer is going to be D, lower and unchanged. Now moving on to actually doing some calculations, and you're almost always going to have a calorimeter calculation. And if you do have that, your formula is NH equals negative MC delta T. The left-hand side is always about what's reacting. The right-hand side is always about the water. So let's start filling some information in. For mass of glucose, we have 6.50 grams, but we need moles. So we'll need to multiply this by the molar mass of glucose. And if you don't remember the glucose formula, you can find it on page 4 or 5 of your data booklet. It's C6H12O6, and that has a molar mass of 180.18 grams per 1 mole. We need to flip that so we can see grams canceling. And then H is what we're solving for. On the right-hand side, all that information about water is there. We have negative 100 grams. Remember that 1 mil is 1 gram when we talk about water, times 4.19, and that unit would be joules per gram degree Celsius, times your temperature change. So taking the difference, you'll get 10.1 degrees Celsius. So we want to solve for H, so we can take this information here and divide it over to the other side, and your H value will be one big number, 117,308. And now based on your units, energy is in joules, but when we come to the answer, we want it in kilojoules. So to get from joules to kilojoules, we just need to divide by 1,000 and we'll get 117. And that's a 3-digit answer. And for that, you just want to make sure that you actually do have what it's asking for. If it's 3 digits, you want 3 digits. And when you're filling this in, remember, start at the left, 117. Keep that last box empty. If you add in a 0 here, it's going to be wrong. So just be careful with that. Now, moving on from here, we have this information asking, again, this one I'm just going to skip just to the question because it's asking which enthalpy diagram could represent equation 2. And if we look at equation 2 only, we have this enthalpy of 508.6. It's on the product side, so that would be exothermic, and your value would be negative. So going through this, I believe the only answer that makes sense is A. And anytime you have an exothermic diagram, it will have that drop between reactants and products, and your value is negative. If you look at the rest, like B is showing endothermic, and then it's also saying negative, which is not true. C is showing endothermic, which if this was endothermic, this could have been right, but because our value is negative, it doesn't work. And this last one has the right shape, but saying positive makes this one wrong. Now, moving on from here, we have asking the enthalpy change of 200 kilojoules is observed by the reaction represented by equation 2. What mass of CO2 would be produced? So in this question, we're using the formula NH equals delta H. And this gets confusing because this H comes from the reaction. It's a molar enthalpy, so we'll divide by the amount of moles we're talking about. And this delta H is the H that is released or absorbed by a reaction. So when we're filling in our information, we'll need to pull out the value from equation 2 and then divide by the amount of moles, which is 2. So I would have N times 508.6 divided by 2, because we have 2 moles, and that will equal 200 kilojoules. And so I'm going to rearrange this and solve for moles. When you do, you'll get your moles equals 0.786. This number keeps going, and then we just want to turn this into grams, so we'll get the grams per 1 mole of carbon dioxide, which is 44.01, and we'll multiply and you'll see your answer is B. So just be careful with this because a lot of students put the released or absorbed in here when it needs to go here, so just be careful. Okay, so moving on from here. Now, this question is now implying about equation 1, and we don't have that information. So that is what we have to do first, because it's asking then about questions about endo and exo. And if we go back up here to equation 1, we don't know the delta H. So if you don't know the delta H to begin with, we don't know if it's endo or exo. But we can find it using what we know, and that would be using page 4 and 5 of your data booklet and using Hess's law short. So when I do this, I would know that my carbon dioxide value, which I would get from my data booklet, is 393.5. Hydrogen by itself is 0, and our HCOOH is negative 425.0. We don't need to multiply these numbers by anything because we have a 1-to-1-to-1 ratio. And then we just have to remember for Hess's law short, delta H of the reaction is the sum of the products minus the sum of the reactants. And this one ends up being, I believe, a negative value, negative 31.5 kilojoules. So what we really want to get from here is that it's exothermic. So we do that quick calculation, we determine that it's exothermic, and then we can start answering the questions based on that. So in exothermic, you release energy to your environment, not absorb. Energy would be included as a product, not a reactant. And then if it's exothermic, that is where we have the drop. And so when it is talking about the potential energy, reactants have more because it's higher up than the products. So that would show with number 7, I believe. Let me just double. Potential energy of the reactants is, yes, is number 7. So this was 2, 3, 6, 7. Okay, and we keep going here. Okay, so now this one, again, 2-part question. And the first one, it's just asking the molar enthalpy for hydrogen in equation 1. So this is just showing that you understand that even though this is the enthalpy of the reaction, if you want the molar enthalpy, you need to take it and divide by 3. So if we do that, you would get, where do I have that? Negative 30.6. And again, 3-digit answer, make sure you have 3 digits, and digits are the numbers, decimals get a box. So this would be 30.6. This positive and negative before it is taking care of that negative value. In the second one, in equation 2, methane contains blank chemical energy than the reactants. So in equation 2, we want to see that this is exothermic. So this is what our exothermic potential energy graphs look like. And methane is a product. So that's here. So if we are looking and comparing methane to its reactants, it has less potential energy because it's lower than its reactants. And then we want to remember, and it doesn't matter what unit you're talking about, all energy originates from the sun. So this would be A. And then the last part here is slightly longer because now we want to figure out the enthalpy change for the reaction that was not given, and we don't have enough information from our data booklet to do Hess's law short. So what we are going to have to do in this case is use these 3 reactions and Hess's law long to solve. So I just want to erase a few things here so I could just write in this area, and then we'll go and take a look at which one's right. So with this, when we're doing this, we know that the one you're trying to find is your target equation. The rest is what we can manipulate. So I'm starting with my first equation, and I have NH3 as a reactant, but in equation 1, I have it as a product. So that tells me that this equation I want to flip. And I also have 2 moles of NH3 in my manipulated and only 1 in my target. So if I want to flip this and divide it by 2, then to show that I need to make this positive and divide it by 2. The next one with methane, same idea, it's on the wrong side. So this reaction we need to flip, but we're happy with the amount because we have 1 mole and 1 mole. And then the very last one, we're happy with the placement, but we only have 1 mole and here we have 2. So we'll need to divide this one by 2. Now, I actually did have this all written out on another page. And if I show that work, I could also see that everything will get canceled out nicely. And then I can add my enthalpies together and I end up with the answer C. So just with that one again, like take a look, flip what you can, divide what you need to, whatever extra in there should all canceled out, and you should be remaining your target equation. Okay. So this next one here, this is another Hess's law short. It's just a little bit harder because we have some moles. So we're going to use Hess's law short, where delta H, and I know there's a longer way to write this, but I just do it nice and short, is going to be the sum of the products minus the sum of the reactants. So it does add in here that assuming the heat of the formation for aqueous glucose will be the same as solid, and that's the value you get from your data booklet. So if I fill in these values, I get negative 1,273.3. And then for this part in here, there's 2 of them, so I'll have to multiply it by 2. So it was negative 277.6. And then with my carbon dioxide, it's going to be 2 times 393.5. And all of those are kilojoules per mole. So I'll add up my products, and then I will subtract my reactants, and you will get the answer B. Moving on from there, now it's asking, or moving into electrochem, seeing what's happening to ethanol. And to be able to determine this, to me, the fastest way would be oxidation numbers. I'm trying to hit the eraser. There we go. So I'm going to assign some oxidation numbers to see what's happening, and then we can compare it to the products and what the question's asking. So let's assign them quickly. This would be -2, +1. Carbon ends up being 0 because we have -2 times 6 is -12, +12. We don't have anything to work with, so it's just 0. On the reactant side, again, or product side, fill in what you know. So hydrogen's always +1, oxygen -2. And then this last carbon is being shared between 2 atoms, and that one ends up being -2, so that the whole compound can add to 0. And in carbon dioxide, oxygen is again -2, and your carbon would be +4. So now when you look at your carbon, you have carbon going from 0 to -2. That is a gaining of electrons, so Rig. So to form your ethanol, that would be reduction. And then the other part for carbon dioxide, it's going from 0 to +4. That's a loss of electrons, so that would have to be oxidation. So we're looking at reduction and then oxidation, and that is going to be D. And let's just keep going here, looking at number 10. Okay, so these I definitely find painful. I probably said this before, because with this, you want to fill in your oxidation numbers. And once you have your oxidation numbers, to be a redox reaction, you must see one going higher, one going lower. So let me show you what I mean here. So for this first part, we get elements by themselves have an oxidation number of 0. And then for hydrogen, we know it's always +1, so chlorine has to be -1. So hydrogen is going from 0 to +1. That's a loss of electrons. And chlorine's going from 0 to -1. That's a gain. So as long as we see that loss and gain, you have a redox reaction. So number 1 is definitely there. So we can rule out number 2 or D. Looking at the next part here, we have... sorry, I need to assign my oxidation numbers. So -2 times 3 is -6. So sulfur has to be +6. -2, +1. -2, +1. So we'd be at -8 plus 2. -8 plus 2 would be -6. So sulfur would have to be +6. So in this one, here's an example where there is no change, right? Sulfur was +6 on the reactant side. It's +6 on the product side. And your oxygens and hydrogens didn't change. So number 2 is not a redox reaction. So now we're looking between B and C for our answers. So let's do the same thing. Assign your numbers. So this one would have to be -3, -2, +1, +1, -3, and then we have -2, +1, and nothing is changing, so that we're not including 3. And so we can be safe and include 4 because it's our last one, and just for the sake of time, we'll skip it. But if you're reading the diploma, do not skip it. Assign your oxidation numbers. Look for one gaining, one getting more negative. Okay, so over here we have this information of H2S, and it's asking during this reaction, hydrogen sulfide is either the reducing or the oxidizing agent, and what is it undergoing. So with this part, to be really quick, I would focus on the just the sulfide. You could do the whole thing with oxidation numbers, but because it's just asking you about the hydrogen sulfide, what you can see is that your sulfur is going from -2 to 0. So it is losing electrons because it's becoming more positive. So if you're losing your electrons, you're undergoing oxidation, and you will be the reducing agent. So for the question, it is the reducing agent, and then it's undergoing oxidation. So we're showing that we understand that. And moving on and keep going here. Okay, so I've probably done a question like this recently, but it always comes up on the diploma, and this is building tables. So when you are building tables, you want to build your table and then use that table to answer questions, and the point is that your table will look like page 7 of your data booklet. So when we're looking at this first one, if you have products, it means you have a reaction. So you can say it's spontaneous, and your OA would be higher than your RA. If you have no evidence of a reaction, that would mean it's non-spontaneous. So your RA would be higher on the table than your OA. So when I do these, I like to just make it look like page 7, right? OAs are on the left, RAs are on the right. Because we're doing it quickly, I usually don't include electrons, even though you can if you want it to look exactly like page 7, but really we just need the placement. So if I look at cobalt going from +2 to no charge, what would be 0, you gained 2 electrons. And if you're gaining, you're undergoing reduction, and you are an OA, which means ND would have to be an RA. It would be losing electrons. We see our products, so your OA is higher on the table than your RA. So I'm going to start by placing that CO2 positive. I want it higher up than ND. Just need to put that a little lower. Sorry about that. ND. And you can also fill in the rest. We know CO2 positive would gain 2 electrons to make CO, and ND2 positive was what would have to gain to make ND. So we can fill that out. Now we can keep going, and we have Y3 positive. Now we don't have any evidence, so you're not totally sure what will happen, but positive charges like to attract negative charges. So this is going to be your OA, which would make ND your RA. No evidence of a reaction means your Y has to be lower. So Y3 positive, MY, we see that your OA is lower than your RA. And then lastly, no evidence of the reaction, and we have the same OA and an RA. Your RA is already placed, so your OA has to be lower than that. And we can say that's SM, and now we're done. Now that it looks like page 7, just without electrons, your strongest OA is top left. As it goes down, it gets weaker. And your strongest RA is bottom right, and as it goes up, it gets weaker. So if we want to list your OAs from strongest to weakest, it would be cobalt 2 positive, then number 6, then number 8, then number 7. So we have 5, 6, 8, 7. Now, also that we have our table, we can take a look here, and the ones that say non-spontaneous means your RA is higher than your OA. So now if I look at this, if I look at A and just placement, Y3 positive is here, SM is here. If that reacts, your OA is higher than your RA, you would have a spontaneous reaction. So it's not A. And I'm going to go just down to the answer, which is C, and just show why it's C. So with this last one, your ND2 positive is here, cobalt is up here, your RA is higher than your OA. This one would end up being non-spontaneous. So if you double check B and C, it would be like A, where your OA is higher up. Okay. Now, this is also a common question on all diplomas, is just asking about oxidation numbers, and it might just pick something within a compound. So in this one, it's for sulfur. So oxygen is always -2. So I'm just going to assign that to first. Hydrogens are +1. And all of these are neutral compounds, so we need our oxidation numbers to add to 0. So for the first one, we have -2, but there's 2 of them. So that would be -4. So sulfur would have to be +4. And we can keep going here. Oxygen in this one is -2 times 3 is -6. So sulfur would have to be +6. In the third one, we have -6 from oxygen plus 2 hydrogens, which would bring us to -4. So sulfur would have to be +4. And then the last one, doing the same thing, we would end up with sulfur getting a 6 again. So with our oxidation numbers, take your time. Just make sure if there's no charge, that once you add in the amount of atoms you have, that your whole equation will add to 0. Okay, number 13 is showing we know how to balance in acidic conditions. And this is another one that will come up in some way. So in this one, your rules for balancing in acidic conditions, balance anything other than hydrogen and oxygen. So we'll put a 2 here because we'll need 2 bromine on each side. Then you add in waters to balance out oxygens. So on the product side, you have 6 water molecules. So on the reactant side, we'll put 6 water molecules. Now with that, we've now introduced hydrogen, and on the reactant side, we have 12. So we'll add 12 hydrogen ions on the product side. And then lastly, you balance charges, which this one's not asking for, but if I wanted to balance it, on the left-hand side, I have no charge, so I have a net charge of 0. To make that the same, I would have to add in 10 electrons. Now in this question, it is asking about your coefficient in front of water and hydrogen, and as we see, that would be D. So we just definitely want to know how to balance in acidic conditions. Now, moving on from here, so at first, when we're looking at this, we are going to have to balance it, but we don't need it to do that for question number 4. What it is asking in here is if this was titrated, what can we expect? Now, this A is the answer, and that is because you are producing hydrogen, so your value would become more, or your solution would become more acidic because hydrogen is being produced. It is a titration, so you wouldn't be decreasing volume. Talking about the electrical conductivity, it wouldn't be decreasing because you're making more ions, so that would be increasing. And this last one about the increase in the intensity of the purple color, well, as you're titrating, that purple color would disappear. So we're not making it more purple, we are making it essentially less in that moment of titration. So it won't be that one either. So if you're looking at any type of question that starts to bring in acidity or something about being basic or pH or pOH, you need to see if hydrogen or hydroxide is being produced. Now with this next part, it does get a bit more complicated because now we're asked to balance. We have to remember that in redox reactions, you must balance based on transfer of electrons, and to do that, you use oxidation numbers. If you don't use it based on oxidation numbers, then you probably won't get it right. Some will work out for you based on inspection, but not always. So we want to be comfortable with this method. So I'm going to start by assigning my numbers. I have -2, +4. I have -2, +7, -2, +1, -2, +6. This is just +2. This is +1. And then you want to see what's changing. So sulfur is going from +4 to +6. That's an exchange of 2 electrons. Mn is going from +7 to +2. That's an exchange of 5 electrons. So to make this the same, we're going to multiply so that we're exchanging 10 electrons. And to represent that, you put the 2 in front of the MnO4 negative and a 5 in front of the SO2. Once you have that, then you balance, because that takes care of the exchange of electrons. Now you balance by inspection. And if I've done the rest correctly, which I think I have, we would get these values here. And the last one I believe was a 4. Let me just double check that. Yes, a 4. Okay. Now we need that balanced chemical equation because now we have to do a stoich calculation. And so we have our known, which is the information of KMnO4, which would be this part of our equation. we need this milliliters to be in liters, so divide by 1,000. So we'll have 0.0315 liters times your concentration. So liters cancel. And now I'm at moles of MnO4. Now I want to multiply by your mole ratio to turn your moles of your known into your unknown. So you have 5 moles of SO2 and 2 moles of the MnO4 ion. So now your moles cancel. And then if we want concentration, your last step is to divide by your volume, and we want that volume to be in liters. So when you're done, you have moles per liter. If you've done this correctly, you will get a pretty small value, 0.00525 moles per liter. And then notice all of your units in your answer is millimoles per liter. So we can pretty much see our answer, but let's just make sure we get it. And to go from moles per liter to millimoles, you need to multiply by 1,000 because there's 1,000 millimoles in 1 mole, and you'll get the value we need to see. Okay, so keep going here. Okay, so now we have some information about a zinc carbon cell. And this first one, without doing much work, we can see that you have a positive cell potential. Positive cell potentials mean you have a voltaic cell. And then based on this one, having this moist salt paste, that is like a salt bridge. And when it's asking about the flow, salt bridges do not have that flow of electrons. They allow for flow of ions because electrons flow from the anode to the cathode via the wire, not the salt bridge. So this one, your answer is B. Okay. Now, the next part, asking about the cathode of the zinc carbon cell. Well, your cathode is where reduction occurs, and reduction is a gain of electrons. So between these two reactions, we see that the zinc is losing electrons because it's on the product side, and your other reaction is gaining electrons because it's on the reactant side. Now, what we're also seeing is that we have some aqueous solutions as a reactant, and so we don't just have a metal rod here, so it needs an inner electrode, which would be carbon. So because it's cathode asking about reduction, it's not going to be zinc, it's going to be carbon. And then when it's asking about electron flow, always anode to the cathode. So your answer here is C. This part over here, now calculating cell potential. So your E of the whole cell is going to be the cathode minus your anode. So the E of the cell was given to you. It is positive 1.50. The cathode is what we want to find because that would be the half reaction at the one that's undergoing reduction. So we don't know that. And we want to subtract the potential at the anode, which is zinc. So you can get this value right from your data booklet. Or I also think was it listed here too? No, it wasn't listed there, but that is in your data booklet. And then you want to isolate your C value. And when you do this, you should get 0.74. So now we know the cell potential at the cathode. Okay, moving on once again. Now, these questions I don't always like. So when you get information that looks like the data booklet, you want to make sure that it's arranged like the data booklet. And if you look at your data booklet starts more positive and then gets more negative. So if this was in the data booklet, you would see equation 2 before you see equation 1. So when it's asking about the half reaction that occurs at the cathode is reduction, and it's going to be your strongest oxidizing agent. And if you go straight from this table, you might be tempted to pick number 1. But if this was actually on page 7 of your data booklet, number 2 would show up first. So your strongest OA is going to be this reaction here, which is B. Moving on to number 19. Now 19 is about reference cells. So if I was to look, and I think I did a similar question beforehand in a different video, so probably one you might not have seen. So if we look at this, this doesn't want to work for me right now. Oh, that's too bad. Okay, that's okay. I'll go back to this in a second. We'll go back to here. So I'm just going to get values from what's happening. So it's asking about equation number 1 and the cadmium half cell. So if I look up the cell potential for cadmium, it is negative 0.40. And from our table talking about equation 1, we have positive 0.58. So when you're looking at cell potential, the differences will still remain the same. So if I take the difference between these two values, it's 0.98. Now what it's telling us that cadmium is going to be the new reference cell. Being the new reference cell means that your new cell potential is 0. The difference between your half reactions still have to be the same, and because this value was higher, it's going to be positive. So anything above the 0 is positive, anything below is negative. So here your answer was D. Moving on to numerical number 8, this is showing you no cell stoich, and in cell stoich you only ever need the half reactions. So I have this half reaction given about ethanol. So I'm looking at this one here. And what I'm using is my formula that moles of electrons equals your amps times your time in seconds divided by Faraday's constant. So with what we're given, we have enough information to figure out moles of electrons. And what I like about cell stoich is you only ever need a half reaction. You don't need everything. So we just need equation 1. So let's plug in what we know. We have 4.00 times 10 to the negative 3. We're going to multiply that by 10 seconds. We're going to divide by Faraday's constant. If you don't remember it, it is in your data booklet on page 3, and it's 9.65 times 10 to the power of 4. So I did this before. The value you get here in your calculator, that's going to be the moles of electrons, right? But it's not asking that. It's asking for mass of methanol. So if you look at your half reaction, we figured out moles of our electrons. That's your known. Now we do the stoich that turns moles of electrons into moles of ethanol by multiplying it by the ratio. So we'll put 4 moles of electrons in the denominator with 1 mole of ethanol. So now the moles of electrons cancel. So again, the answer you get here will go right here. Multiply it by 1 divided by 4, and now we have moles of ethanol, but we don't want moles, we want mass. So your last step is to get the molar mass of ethanol, which is 46.08. You plug that all in, and you get a pretty small number. It's going to be 7.78 times, oh, sorry, that's supposed to be a 4. 4.78 times 10 to the negative 6. So when you're filling this in, it's going to be 4786. All right. Okay. Now coming here, comparing voltaic cells to electrolytic. So we know this voltaic has to have a positive cell potential. It does convert chemical to electrical. So this isn't right. This is. Electrons will move towards, nope, electrons move from the anode to the cathode, so that's not right. Requires a salt bridge. So we're ruling out A and C, but we could rule out more, so let's keep going. So electrolytic is not spontaneous. This was already moved out. Moves anions towards the cathode. This is not true. Anions move towards the anode. Reduces the strongest oxidizing agent. That's true. But that happens at the cathode, and requires a power source. That's true. So this one, the answer is D. So this is just based on the theory of voltaic and electrolytic. Now moving on to this here, we have some information, and then it's asked about the half reaction of OH negative. So what I like with this one is, and I think I might be overdoing it in this one, but just writing out what I have reacting. So I have Ag2S, which is an OA. You have OH by itself, which is ARA. You have Na positive, which is an OA. And you have water, which is both. Now, your strongest Ra happens to be hydroxide. And if it's undergoing or acting as a Ra, it's undergoing oxidation, which means we have to flip that reaction. So the one that works out is A. And this next one, which of the following metals will act spontaneously? So I'm having trouble with my data booklet, but what you would see on page 7 is you would find silver iodide. So silver is Ag. Silver iodide is higher as an OA than silver sulfide. So why do I keep doing that? Ag2S. So when it's asking what can spontaneously act as a reducing agent with silver iodide, but not with silver sulfide, if it's a spontaneous reaction, your OA is about your Ra. So we're looking for an Ra that's between these two compounds. So we would find that, I'm just going to write it out here, that nickel and cobalt, so nickel would be on the side and cobalt would be on the side, that can act spontaneously with silver iodide. But if you react it with Ag2S, it would be a non-spontaneous reaction because now your Ra would be above your OA. So the rest wouldn't work out, and you could double check that. But yeah, with this, you would be looking for the Ra in between. Okay, so looking at a little bit of organic now. So I do know I have a few of these done on a different video, so I'm sorry if it's a bit repetitive, but it's still a good review. So asking about the parent chain, you're looking for your longest chain possible. So if I just took a quick peek, my longest chain possible is what I've just drawn in. And if you count all those carbons, it is going to be 9. So that would be non-ane. Looking at this next one, we have some information about the molecule. And then you want to classify it. Because of the benzene ring, it's going to be aromatic. So if you don't have a benzene ring, you just choose aliphatic. And then based on your functional group, so just looking at what we have, this one here is a carboxylic acid. So that would be D. Number 9. So this one, again, I do recognize it from a different video, but here it's nice because as long as you understand what a few compounds do, you could figure this out because depending on what you choose makes you right. So for instance, I can remember that octane is a vehicle for fuel, fuel for vehicles. So that would be 1 and 5. So you're just using a combination of what you would know to be right. So another one I know is about methanol. Methanol is number 3, and it is used as an antifreeze. So when you are studying, and you probably have, like I would in my class, I would have information about it, and when you're studying, you might just glaze it over. Just make sure you're reading it, because I am noticing that this being able to recognize what some organic compounds do is making its way into the diploma more and more. So you just want to take your time with that. All right, so moving on. Again, I believe this question came up before as well, but you have this chart, and then you have to interpret some value or some information. So if you look at this chart, you'll notice that as you're adding branches, your boiling point gets smaller. And you can read this over, but you will see it. So in this one, your answer is your boiling point decreases as your branching increases. So that would be A. Now the other part I'm just going to point out here, because this is going to come up in a moment, is that depending where your OH group is, your boiling point also decreases and you become more soluble. So keep that in mind when we come back to it in a moment. Now it's asking about compound 2, what we can form when but2-ene reacts. I'm sorry. Compound 2 can form when but2-ene reacts. So but2-ene means you have a double bond between carbons 2 and 3, and then the rest of these would have hydrogens. And 1, 2, so these just need 1 and this needs 3. And then if you want to form compound 2 is this one here. So you notice that the double bond is broken and you only have one bromide there. So if I go back here, if I want to break a double bond, that's going to be an addition reaction. So it's not going to be either of these. And if this bond breaks, that means that carbon 2 and carbon 3 both can bond to one other atom. Now, when you take a look at the molecule, because you only have one bromine, it can't be Br2, because if you had that, you would have had Br2 over here as well, but we don't. We only have one. So it has to be HBr. So the answer here was D. Now, coming back to this last one that was mentioned. So looking at solubility from most soluble to least soluble, compound 2 is definitely least soluble because it has no OH group, which would make the compound soluble because that makes it polar. And then it's now going to be about those branches. So as mentioned, the more branches you have, the more polar you are. So the most amount of branches is number 3, then number 1, and then number 4. And I should also say not just the branches, but placement. So that was 3, 1, 4, 2. Okay, now this is definitely, just want to add on here, something I have not taught in class, but it makes me feel a little bit better that I didn't actually miss it because it was given this information and you had to interpolate. So we had to do that in a few. So we just want to make sure that we understand those trends and can read the trend. Now, moving on to this next one, and I know I've done this one before as well, kind of recently, asking about what is not an isomer. So if you are an isomer, you have 10 carbons and 16 hydrogens. If you're not an isomer, you don't have that formula. So I'm just going to skip to the answer just to save us some time, and that is C, and showing the understanding. So you do have a benzene ring here. So if I drew this out, and benzene rings have alternating double bonds. And then we have this happening. So carbons are easier to distinguish. So we have a carbon here, 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 and here. So if you counted them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that still has 10 carbons, so that's good. But now we want to count our hydrogens. So this hydrogen on the end can bond to 3 other atoms. So there would be 3 here, 3 here. This carbon has 2 lines coming from it. All carbons can have 4 lines, so it has 2. So this one would also have 2. This carbon here has 1, 2, 3, 4 lines. Same with this one. So neither of these have any hydrogens. Over here, this carbon has 3 lines, so it would have 1. This one would have 1, 1, and 1. Now we can count. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this is H14. Because of that, that's the odd one out. The rest of them would have the C10H16. The other part here is asking about the amount of double-double bonds. And I do think the easiest thing for me to see this one was just to try and draw it. And even though I don't know what it looks like, I do know that I have 10 carbons altogether. So 1, 2, 3, 4, 5, 6, 7, 8, 4, 9, 10. And I have 16 hydrogens to place. Organic molecules like to be symmetrical, so I'm just going to start by placing my hydrogens. So now I've placed 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So all the carbons that I filled in, so this one, this one, this one, this one, these ones, they're happy. They all have 4 lines. But the carbons in the middle don't. So they want to start sharing. So we would have some double bonds happening so that we would get the 4 lines. I just want to double check here. 1, 2, 3. That your answer is B. Why does that look? 1, 2, 3. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep, that one works out. Okay, moving on. Again, a little bit repetitive. I feel like this ended up being something I did earlier. So here, looking at propane can be recovered. Propane, we could probably figure out how to get it from the rest, but because of the process, we have to pick which one we want to use. And our crude oil would contain propane. So crude oil is a mixture of hydrocarbons. Propane would be one of them, and that comes out by fractional distillation. So if you're unfamiliar, just take a look at that. That is in your textbook, and you probably have a video on it that shows that you're breaking up those hydrocarbons using boiling points. And now the other part, propane reacts with chlorine gas. So if you drew out propane, it looks like this. And we would have some hydrogens. I'm just being lazy and not drawing it in. And if you're reacting with chlorine gas, Cl2, what we're going to end up having is, what are we doing here? Chlorine gas. So it's not going to be an elimination reaction, because elimination means you are forming a double bond. I think I read something wrong. Propane reacts with chlorine. Yep. To produce to produce hydrogen chloride. So because you're producing HCl, that means one of these chlorines swap places with a hydrogen to produce this, and compound 1. So we'd have a substitution reaction, which makes sense because that was our option. And we're not forming a double bond, so you can rule out number 2, and it would be number 1. I had to think about that one for a second, even though I know I've done it before. Ethyl propanoate, that would be an ester, and esters are formed by the alcohol and the carboxylic acid. The first part of the name comes from the alcohol, so that would be ethanol, so we can rule out the last 2. And the second part comes from the carboxylic acid, and that one is showing D. This is another one we have done recently, and this is just showing we know the definition at equilibrium, and everything here has to be constant except mass is one that's not an observation, so that's one that's not right. The other 3 do work for a system that's in equilibrium. And then about your stresses, so if you add hydrogen, right, if we add in, you shift away, so you'd be shifting left. And here they're asking about shifting towards the reactants, so we're shifting left. So number 1 would work. Adding CO2 over here, shift away would shift towards products, so that won't work. Catalysts don't do anything for the shift. Removing CO, if you take it out, you shift towards, so it won't be that one. Removing CH4, so we take it out, we shift towards, that will work. And then decreasing the volume, if you decrease the volume, you move to the side with less moles, and we have less moles on the reactant side. So we have 1, then 5, and 6. Okay, let's keep going. Again, I've done a question like this. I'm just going to skip that one for now. I do like this last one that I know I've recently done as well in one of my last videos. And this is just showing that we understand ice and how our Kc expression comes about. So in this question, if I look at that first reaction that was listed right over here and set up an ice chart, what I would see, and I'm sorry if that's making you not feel too good, if I started with 1 mole per liter here, 1 mole per liter with the CO2, and then I would produce, or I initially would have nothing, and then I would have, based on the mole ratio, I'd have minus x, and this was plus 2x plus 2x. Now, I add my columns. I would have 1.0 minus x, 1.0 minus x, 2x, and 2x. Now, this is at equilibrium, so this goes into the Kc expression. But if I go back up here for a moment and set up my Kc expression, so my 2's are coming from the coefficients, my Kc expression is the concentration of CO squared times the concentration of H2 squared divided by the concentration of CO2 times the concentration of CH4. So what I'm filling in at equilibrium, I need to square. So I come back down here just to do that, which I'm sorry for going back and forth like this, but these are the values. So 2x squared times 2x squared, sorry, over here, divided by your 1.0 minus x, and that would be times 1.0 minus x, and that would all equal the Kc that was given to us. And now when we're taking a look at which matches, the one that matches is B, because this part on the bottom can be written as just itself squared, and then we'll have our answer. Okay, keep going. We're getting closer to the end here. So we have this information. Oh, this one's actually nice and easy. We just need to calculate Kc. And so we're setting up that expression, and your Kc expression is the concentration of CH3OH divided by the concentration of CO times the concentration of H2 squared because of that 2. So now we have the expression. We're going to fill in the values. So you'll have 2.75 divided by 0.75 times 1.25 squared. And once you plug that into your calculator, you should get C. Oops, sorry, what's happening here? Okay, now this other one, heating the system. If you heated your system, knowing that this is exothermic, if we added it, we'd have to put it on the product side. So if you heat your system, you are going to shift away. So you're going to shift towards the reactants because it started on the product side, shift away. And then the only thing that can affect Kc is temperature. And if you're shifting towards the reactants, you have more reactants, and that means your Kc value gets decreased. So Kc represents the products. The more Kc or more products you have, higher Kc it is. So in this case, reactant side decreasing. All right, so moving on from here, number 13, what do we have happening? Oh, this is an ICE question. So we have some information. We have the chemical equation. It tells us initially what we have. So if I set up ICE, so initial of CS2 is 0.18 moles per liter. Initial of hydrogen is 0.31. And then for products, you can assume 0 unless it tells you otherwise. Change based on the mole ratio, so minus x minus 4x. Products are being formed, so plus x plus 2x. Now add your columns, you get 0.18 minus x, 0.31 minus 4x, and then you'd still have these two here, x and 2x, but we actually don't need that for the question. Now in this, it tells you at equilibrium that your information about the CS2 equals 0.13. So we can take the 0.18 minus x and set it equal to 0.13 and then solve for x. When you do this, you'll find out that x equals 0.05. And then the question's asking you about hydrogen at equilibrium. So now that we know what x equals, we can take the information about hydrogen, plug it in, and solve, and you will get 0.11. Okay, so this is a 3-digit answer when you're plugging this in, right? 0 gets a box, decimal get a box, 1 and 1. We're still showing 3 digits, 0 would be a digit. Number 35, looking at H2BO3, which is this one, and a different compound that would form a conjugate acid-base pair. So to be a conjugate acid to a conjugate base, you're a difference of just one hydrogen. So when we're looking at what we have, the difference of just one hydrogen could be 1 or 3. So we're looking not at just this last one. Where did my pen go? And now it just stopped. Okay, I'm going to have to pause it here and do a part 2. So if you watched up to this point, thanks for staying with me because I know this has taken a very long time, and I will post part 2 shortly. So again, thank you for watching. If you have found this helpful, please subscribe. And if you are writing your diploma on Tuesday, best of luck to you. And if there's anything I can explain again or explain in more detail, please just leave me a comment and I would be more than happy to. As always, thank you for watching.